We're going to deal with a couple of different quantities here, a couple of different ideas. We're going to deal with the idea of energy and the idea of work, and they are related. So at the end, I want you to kind of summarize what is the relationship between energy and work, but also I want you to know, what is energy? Energy. What is energy? All right. Well, this is a banana. And this banana has energy. And the energy contained in this banana has gone through an amazing journey. It started hundreds of thousands of years ago, maybe, in the core of our sun, in our solar system. The temperature and pressure at the center of our sun is so intense that it's able to force hydrogen, or force protons, hydrogen nuclei, able to smash them together and overcome the repulsive forces between protons and squeeze them together so that that nuclear force can overtake and we can create helium. So it takes hydrogen, converts it into helium, and in the process releases a huge amount of this stuff that we call energy. But it's in the core of the sun. And it's a long way to the surface of the sun. And so it makes its way through one layer of the sun called the radiation zone. And then it gets cooler. The sun gets cooler as you go out. It's still super, super hot, but it's getting less super, super hot as you go out, till it's finally able to that energy is transported to the surface of the sun through convection. And then it reaches what's called the photosphere of the sun. And the photosphere is where the photons, these little packets of pure energy we're going to learn about later, are away from enough material that they can just radiate out into space. And it takes thousands of years on average for the photons, for the energy that's created in the core of the sun, to make its way to the surface. And then it takes about 9 minutes or so to reach Earth. And somewhere, well, there's no label on this banana, somewhere in probably Central America or South America, it landed, some of those photons landed on a banana tree. And these banana trees have leaves, and these leaves have chloroplasts, and take biology, you'll learn about that, but they capture the energy that is in that photon, and they store it in molecules, the molecules of this banana. Okay? And you can think of, now by the way, let me teach you something that has nothing to do with physics. I want to show you the proper way to peel a banana. People think that this is the end. No, that is wrong. This will be on the test. You take this end, you pinch it with and then you pull it back, and you peel it like this. See? Isn't that nice? Okay. Now that way, see this little nubby thing on the end? That way you don't have to deal with it. And when you get to the end of the banana, it's just perfection at the very end. So that's why I like a happy ending. So that's why I peel a banana this way. So anyway, now I'm going to take this banana. Now in the atoms and molecules of this atom, or of this banana, they've been arranged in such a way, they've kind of been squeezed together and locked into place. This is chemistry. So that the energy is, kind of think of the molecules as in an arrangement where there's lots of little springs that want to push them apart, but they're locked into place in these mainly sugar molecules, right? You learned about sugar and sucrose and all that kind of stuff. So what I'm going to do is this. I haven't really eaten yet today, so I'm going to eat this banana. Now what's happening right now is this. I am chewing, I'm mashing it up, mixing it up with saliva and stuff. It's not gross, it's life. Now we'll get to the gross part soon enough. All right, now, so I've just eaten a fraction of this banana. And I'm swallowing it, and it's going into my stomach, where basically it's kind of, it's mixed up with a bunch of acid and stuff in your stomach. I think mainly the acid is there to kill all the germs so you don't get sick. But it gets it ready. It mashes it up. It gushes it all into this pasty stuff. And then it gets sent into the small intestine. And the banana goes through all the small intestine, wraps around, no questions for this part, goes around through your small intestine. And then those molecules are actually absorbed and put into the bloodstream. And now all this energy that's locked in the molecules of this banana is now dispersed into your body. And now your body can use this energy to do things. And that's what energy is. Energy is something that allows you to do things. And it goes to the body. Now I can talk, I can walk, I can do all these things. I mean, what would happen if I stopped eating? I would get hungry, because that's nature's way of saying, you need to eat something because this ain't good. Then, if you go a long time without food, you start feeling weak and tired, and your body starts shutting itself down. Because all of you have ancestors that had to survive a famine at one time. So your bodies had to stop, slow down the metabolism. That's why one reason it's so hard to lose weight. Because if you try to lose weight by not eating, your body just says, I want food, and then it slows down its metabolism so that you aren't burning off that energy as fast, and it's hard. Now, then eventually, if you don't get enough food, you'll die. And if you're dead, you can't do anything. See, that's kind of by definition, right? You can't do anything. So energy, we have I have this definition for energy. Energy is the measurable capacity to make change in the environment. Okay? That's what energy is. Energy is the capacity that we can measure. There's different ways of measuring, but we can measure, and it gives you the ability to change your environment. Now, I did a little demonstration before the lecture, right? Where, if I hold something over your head, a rock or something over your head, that rock that's held over your head, it can make change to your environment, right? There's energy there. If a baseball is moving towards your face at 100 miles an hour, that baseball can change your environment, the environment of your face. Now, if it's not moving at all, it can't make change, right? If the rock doesn't have any height over your head, it can't make change. And if these molecules aren't arranged properly, they can't make change. You can't have chemical reactions that release energy. So it's all around us. Energy. The capacity to make change in the environment. That is the way to think about what energy is. Your car needs energy. Now, my car plugs in. I take energy from the electrical grid and store it in the battery of my car, and then I use it. Most of you still have internal combustion engine cars where the energy is stored in the gasoline, in the molecules of the gasoline, and then we have, combustion takes place, and we figure out how to make things happen. So here's the thing about energy. There's two things about energy. Energy can be stored. You can store up energy. If something is moving, really fast. There's energy stored in its motion. We call that kinetic energy. It's the energy stored in motion. I already wrote the word stored, so that's energy stored in motion. If I hold a rock over your head, there's energy stored in the gravitational field. Gravity wants to pull it down and then smack you in the head or something. Okay, so that's called gravitational potential energy. We're going to learn about that. There's an equation for it. We'll get to the equations later. Oh, one thing I forgot to mention earlier. If I have a rubber band, here's the rubber band. It's just laying there. Really can't do anything. But if I take that rubber band and I stretch it, can it do stuff now? Can it change the environment? Yeah. Poof. Okay. I shot it across my desk. Wow. All right. So have you ever gone up to your little sibling or something and go like that? Yeah. That's a good use of energy. All right. That affects change in the environment. Okay. We call that elastic potential energy. That's the energy stored in a elastic material. Springs, right? Springs, or anything that will bend and then come back to its shape. We can store energy in that. Now, bananas. That's food. Gasoline in a car. Lithium ions in a battery, the way the molecules are arranged, we can store energy that way. That's called chemical potential energy. And if you take chemistry, you learn all about that. And there are other ways to store energy, by the way. This isn't the only thing. Okay. But these are the main ways we're going to study, at least in this unit. Now, but energy that's stored isn't really doing anything. If you want to see change, you have to transfer energy. Every change that you observe, whether people walking around, turning the lights on and off, you jumping up and down, you throw things at each other, whatever, all those changes are energy that's being transferred. Now, we're going to get to this later in the year. Energy can be transferred using waves. Light and sound. You can transfer, you can affect change in the environment. I'm affecting change using sound right now. Right? I'm talking, I'm sending energy out through the air in sound waves. It's wiggling your eardrums and it's changing your brain a little bit right now, some of you that are awake. That's one way to do that. I could put something on a stove. That's called heating. Heating is a way of transferring energy from one system into another. If you dip your hand into a pot of boiling water, there will be change to your environment. Not good change. So that's one way that energy is transferred. See, but the way that we're going to what we're going to study today, what we're going to talk about today, where energy is transferred, is called working. Working or work. And this is mainly what we're going to study right now is work. Okay, so let's talk about what is work. Okay, well, work is the transfer of energy through the application of a force. Okay, for example, if I, where'd my baseball go? Can you hand me my baseball? It's right over there. So here's a baseball. If I want this baseball, if I apply a force to this baseball, I can change its motion. Okay, and so obviously by pushing on something, I can change it. I'm changing its motion back and forth. Okay, so I'm doing what's called work when I do that. And I'm basically, here's kinetic energy, right? It's the energy due to motion. Well, the ball is not moving, is it? This ball is not moving, but if I apply a little force to it, not very much, a little force, now it is moving. And now it can. So what did I have to do? I had to transfer energy from my hand. Now what kind of energy, by the way, what kind of energy does my arm have? Okay, look at this bad boy right here, okay? Muscular energy, yeah. No, it's chemical potential energy in my muscles. Okay, so because I ate food, here's the banana. Nom, 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 nom. Okay, now it's being spread throughout my body. Now my body has energy. Now I can transfer energy out of my body and into the ball by pushing on it. When you throw a baseball, you are giving it some of your energy. You're transferring energy out of your arm and into the ball. And now that ball can do things. So it's a transfer of energy. Work is a transfer of energy by pushing or pulling on things. Okay, now, couple of things though. We have a way of calculating this. And that is it. Let's see. Suppose I have a crate like this. We love crates. Physicists love crates. Here's a crate on wheels, so we're going to say there's no friction. There's someone pushing on it. They're going to push on it with a force. Now let's say they're just pushing on it, but it doesn't move. Okay, and I want to use the document camera for all this stuff. I can get up and demonstrate it later, but here I've got a little box right here. Here's my little box, little crate. Now what if I push on this? But it's not moving. Have I changed this thing at all? No. I didn't change it. I didn't change this. So I didn't transfer any energy into it. So in order for the force to have transferred energy into the object has to change its motion. It has to change where it is. I have to displace it. Like that. Now I did work. See, there's change. This little box, the box is here. I push on it. I've changed where it is. I made a change. So there had to be a transfer of energy. So here's how we define work. Work equals the force that I apply to it times the distance it goes, or actually the displacement. I'm going to be official here, displacement. Work equals force times displacement. All right. So, look, and what we mean here, when I say work, by this person, if this person is pushing on this crate and it doesn't move, you're not transferring any energy into the crate. Okay? But if you do push on it and it starts to accelerate and you displace it, you have done work. You have transferred energy, chemical potential energy in your body to the motion of the crate, to kinetic energy. Or alternatively, if I apply a force to this and I lift it up, I've given it height, I transferred gravitational potential energy into it through the application of a force. So I did work. And so we use work as a way, because it's really easy to calculate the work. It's force times displacement. Now, let's take a look at units here. This is our definition of work. Work equals force times displacement. By the way, this is a very simple, we're going to get to a more sophisticated definition here in a minute. But before we do that, let's take a look at this force. What units is force measured in? Newtons. And what is displacement measured in? Meters. And so we have a Newton times a meter. And when we multiply newtons times meters, we get the unit of energy that we're going to use in physics. A Newton times a meter, by definition, actually, a Newton times a meter is called a joule. A joule is the fundamental unit of energy in physics. You know, now later on we'll deal with kilojoules or megajoules and that sort of thing. But so here we have newtons times meters. A Newton times a meter equals a joule. We use a capital J, not a lowercase j, a capital J to represent work. So in this case, we have this little dude here pushing. Let's say, he or she is pushing on this with 50 newtons. That's a good little push. And maybe this thing changes. It goes from here to here. 3 meters. Well, how much energy was transferred out of this person into the crate because it moved? Well, we say that work equals a force times a displacement. Well, this is 50 newtons times 3 meters. Well, 3 times 50 is just 150. And a Newton times a meter is a joule. It's that easy. So we say the person did 150 joules of work on the crate. But here's what I want you to think about. I want you to think, oh, this person transferred 150 joules out of their body and into the crate through the application of a force, through a displacement. Okay? That make sense? Now, it gets a little bit more complicated, though. What if this person, let me redraw it. What if this person, and I'm not going to draw the person again, I'm just going to draw the force. What if I push down on this crate like this? Oh, I'm sorry, off screen. What if I push down on this crate with a force like this? Well, let me put, this is our force. And let's say the crate does displace, here's our delta x, goes from there to there, but the force looks like this. It's at an angle, right? Now, we can take forces and break them up into their components. So here's the parallel component, and here's the normal component. Zoom in a little bit. Now, let me ask, what did this force do? This component of the force. All it did is push the crate down. But did the crate displace down? No. Now, there is a normal force here, and what it did is it increased the normal force on the crate. But what really affected the change to the crate? Did this change the crate? I mean, what if all you did was take this crate and push down on it? Are you going to change the crate? No. Crate didn't change. Unless you push down on it so hard that you broke and crushed the crate, right? But then you are getting a displacement, right? As you crush it down, you are displacing it down. So yeah, you're good. That would be a change. But if the crate, you just push down on a little bit, it's not changing. There's no downward displacement. What is causing the displacement here? What is causing the change? Just this component of it. So really, what we say, it's that work is equal to force times displacement, but really it's the force that's parallel to the displacement. Does that little symbol make sense to you, that little parallel symbol? It's the force that's parallel to the displacement that does the work. Well, what if we measured this angle? So, well, here's a force, and here's our displacement. So let me kind of redraw that. Here's our force vector. Now let me hook up the displacement vector to the force vector. I'm going to take this and hook it up here. So here's our displacement, like that. So this angle, here's our force vector, here's our displacement vector. So there's the angle between the force vector and the displacement vector. So so we want this component. So here's the force that's in the x direction. Here's our delta x. So what is this component of the force in terms of the angle and the actual total force? Well, this makes a little right triangle, doesn't it? So what is the adjacent leg equal to? F times what? In terms of the angle. The adjacent leg is the hypotenuse times the what? Yep. Not cosecant. Who said cosecant? No! Cosine! Oh my God. That was Jawed. All right. You're immortal now. All right, so look. So really, another way of expressing the work is we say that the work done, that is the energy transferred from the pusher to the pushy, is equal to the force times the cosine theta. And what is theta? Theta is the angle between the force and the displacement vectors, like that. Now I'm going to rearrange this. This is the total force, this is the displacement, times the cosine of the angle between them. Now, so this is really our basic equation for work. Work equals force times displacement times the cosine of the angle between the force and displacement. Now, here's something kind of interesting. Look up here. The force is a vector, isn't it? Displacement is a vector. But work is a scalar. Work doesn't have direction associated with it. You would not say, oh, I did 50 joules or 150 joules of work to the west, because it doesn't matter what and so work and energy itself, right? Work and energy are scalar quantities. Now, have any of you in your math classes done what's called the scalar product? Have you done any vector mathematics in your math classes yet?
Yeah.
And remember the dot product?
Oh, yeah.
Okay, now by the way, if you haven't had that yet, don't worry about it. But another way of explaining work, when you have a quantity that's a vector times another quantity that's a vector times the cosine of the angle between them, and the answer is a scalar, we call it the scalar product of two vectors. Remember that big dot? Did you learn about the big dot in your math classes? So work is the dot product between force and displacement. Now, if you haven't had that math yet, don't worry about it, because this is what you need to put on your, your equation list, and this is what you need to know to solve problems. But when you're doing work like this, you are transferring energy from one system into another system. Okay. Now, one other thing, the last thing we're going to go over. What happens, now this is all great, like look at this super simple problem that we had here. It's just force times, they were parallel and all that, so they just multiplied and you got this, but the force was a constant. What if the force varies? What if the force changes with position? Well, that's what we're going to work by a varying force. Well, let me give you a problem. Let's say we have a constant force. So, example. Let's say we had a force that's equal to 5 newtons. And we have a displacement of, and let's say it's all in the x direction. And we have a delta x of 4 meters. And we want to find the work done. Oh, by the way, we can say theta, the angle between the force and displacement is 0 degrees. Okay. And I want to find the work. So let's solve. Well, you would use, work equals force times displacement times the cosine of the angle between them. So the energy transferred by the application of a force will be equal to 5 newtons times 4 meters. And I look at the angle, cosine of 0 degrees. What is the cosine of 0?
1.
1. Yeah, you get. Okay. So this is 1. So 5 times 4. So you say, okay, the work is equal to 5 times 4 is 20. A Newton times a meter is a joule. Yay, we solved the problem. But I'm going to solve it a different way now, a much dumber way. I'm going to graph it. What if I plot force in newtons as a function of displacement in meters? So 1, 2, 3, 4, 5. And then 1, 2, 3, 4. Well, in this problem, the force was not varying. It was just 5 newtons the whole time. Okay? And I want you to look at this. We've done this before in when we were studying kinematics. Do you see that this is a rectangle? And what's the area of that rectangle? Well, how do you calculate the area of a rectangle? Like base times height, right? So what is the base times the height here?
5 times 4.
Which is what?
20.
So the area equals 20. 20 what? Well, what do we multiply together? A Newton times a meter, so that means joules. So if we let's look at one little square. Here's one little square in here. That one little square of area, okay, well, this has a width of 1 meter and has a height of 1 Newton. Well, 1 times 1 is 1, and a Newton times a meter is a joule, so each little square is 1 joule. Does that make sense? Okay. Well, what if the force was not a constant? What if I gave you this? So 1, 2, 3, 4, that's the same. And this is our displacement in meters. And then we have 1, 2, 3, 4, 5. This is the force in newtons on our object. But what if the force did this? What if it's like a stretchy material, like a rubber band? And when we're not stretched at all, it is applying no force. But what if to pull on it, oh, now I have to pull a force. But now I have to have a greater force, and a greater force, and a greater force, and a greater force, and a greater... Oh, I broke it. Yeah, oh well. What if the force did this? So, what if the force varied? How much work did it do? Well, here's a little square. Let's take a look at a little square. Here's 1 joule. And then, oh, here's another joule. And here's another joule. I think that's 1 1/4 right there. But so I can just count the squares underneath, but then I get over here and they're all off a little bit. So how do I figure out the total area underneath here? Well, the total area, I'm sorry, that's the point. The total area underneath there is how much work was done by that weird varying force. Does that make sense? Okay. So what is the area of this? Well, it's a triangle, so it's 1/2 the base times the height. Well, that's 1/2 the base is 4 meters, and the height is 5 newtons. So 4 times 5 is 20, divided by 2 is 10. 10 a Newton times a meter is a joule. 10 joules of work was done. And that makes sense because all I did from this graph to this graph, I just cut this in half, right? You take a rectangle and you just cut it in half. and that's your triangle. Okay. Now, if you have a force like this, and I'm not going to put numbers on it because I've been talking too long already, but if you have a force times your displacement versus your what if a force did this, and then it stayed constant, and then it did this, and then it stayed constant again, and then it did this? Well, how much work did that force do? Oh, you add up all the area underneath there. Okay, here's a triangle, rectangle, triangle, rectangle, rectangle, triangle. So you got to add up all those little rectangles and triangles. But the total area under here is the work done. So we can say that the area under a force versus displacement graph gives you the work done. Okay. Now I've talked too long already, so I'm going to stop here. But and some of the homework problems get a little bit more complicated than just like having one force on it. So, but most of them will involve you figuring out how much work was done by force. And you have to look at this. You have to look at the force, the displacement, and the cosine of the angle between them. Now, what if the angle between the force and displacement is 180 degrees? In other words, what if the force is in the opposite direction as the displacement? Well, that force is trying to slow the object down. And it's actually going to do negative work because the cosine of 180 degrees is -1. And it's going to do negative work. It's going to try to take the energy away from. It's transferring energy out of your moving object. But this is really interesting stuff. I'm really glad we're starting this new unit. Okay, so let's just quickly review. Energy is the measurable capacity to make change in the environment. Now, energy is stored in nature in various ways, but when you really want to see something happen, when you want to see change, energy has to be transferred through waves, through heating, or through work. And we define work to be a force times displacement, newtons times meter. That gives us the units of joules. But the force, it has to be the force that's parallel to the displacement that actually does the work. Work and energy are scalar quantities. They don't have direction associated with them. And if you graph force as a function of displacement, the area underneath that graph gives you the work done by that force. Woo! That's a lot. Any questions? That is all.